Hello, everyone. This is Guannan from Purdue University, and today I'm going to talk about our paper on compiling symbolic execution with staging and algebraic effects. This is the joint work with Oliver, Shangyin, and Tiark. So symbolic execution is a technique to translate programs to symbolic expressions and pass conditions that express the constraint on those symbolic expressions. For example, here's a simple program where x and y are both symbolic inputs, and this simple program has 3 paths in total. Each of the paths has its own constraint. For example, this constraint x less or equal than y corresponds to the first condition encountered during the execution. And a symbolic execution engine is a tool or artifact that does this translation from programs to logical expressions. There are many popular symbolic execution engines for various programming languages, from high-level or to low-level languages, and they are shown to be very useful in software testing, bug finding, program analysis, and verification. Here you may find your favorite ones. But however, building a such symbolic execution engine is often considered very hard, especially for general purpose programming languages. Why it is hard? Here, among the many challenges, we identify 3 major requirements when building the symbolic execution engines. First, the symbolic execution semantics and engine has to correctly model the concrete semantics, which serves as the ground truth of program execution. Second, it is very much preferred that the engine can execute the program efficiently with or without symbolic values. This is very important when the total number of paths to be explored is exponential. Third, when exhaustive execution is not possible, we want certain flexibility. Of course, there are many different aspects of flexibility, but here what I mean is we can use different strategies for path selection or heuristics, and many existing approaches can actually satisfy 1 or 2 of those requirements. For example, instrumentation-based approaches can achieve great performance, but it's hard to argue its semantic clarity. And interpretation-based approaches usually have poor performance compared with its instrumentation-based approaches. However, overall it is hard to achieve those 3 requirements at the same time. In this talk, I will describe our approach, that is a semantics-first approach to building symbolic execution engines by using definition interpreters with multi-stage programming and algebraic effects, in which the combination of those satisfies those requirements at the same time. So this figure shows an overview of our approach. We start from a definition interpreter and refactor it to a symbolic definition interpreter, and further to a staged symbolic definition interpreter. Then we can use it as a compiler, which generates the code that performs symbolic execution. Let's zoom in a little bit, starting from the leftmost ones. Our starting point is a concrete definition interpreter. Let's consider a simple imperative language for doing symbolic execution. This figure shows the grammar of the language, which is quite standard. We have assignments, conditionals, loops, sequential statements. And we also have I/O operations to write and read numbers. Then we define the definition interpreter using algebraic effects. That is, the interpreter here can use the state effect and I/O effect. The state effect carries a store, which is a mapping from variables to values, and it models the memory during execution. At first approximation, this interpreter is very similar to monadics interpreter you may be familiar with. For example, the interpretation of assignments is to first evaluate the expression E to a value V, and then get the current store sigma, and then put the updated store back to the state effect. Note that here we just use the declared effect operation put and get, which are in color blue, but we have not given the meaning of those operations yet, and later we'll come back and talk more about effects and handlers, which gives the interpretation of those algebraic effect operations. The next step is to refactor the concrete interpreter to a symbolic interpreter. This can be done by first allowing symbolic expressions to be values, and then changing the state effect to carry a pair of store and a set of path conditions. And we will collect path conditions during the symbolic execution. We also need to introduce 2 additional effects, that is the non-determinant effect and the SMT effect, which are useful for symbolic execution. The non-determinant effect is used to model the semantics of exploring multiple passes in symbolic execution, and SMT effects models the solver invocations. For example, a simplified version to interpret conditionals is to non-deterministically execute both branches S1 and S2 here when the condition cannot be determined to a Boolean value, true or false. And this operation choice in color blue is an algebraic effect operation and is part of the non-determinism effect. Then we use multi-stage programming to turn a symbolic interpreter into a compiler, that is a staged symbolic definition interpreter. To do that, we first perform a manual binding time analysis, that is to identify and annotate which parts of the computation happen statically and which part happens dynamically. By static computation, I mean those only depends on the input program AST, and dynamic parts are underlined in our notation. And those represent the runtime computation and will be generated as a residual program. The algebraic effects and handling them actually can pose a significant overhead during execution. So due to the performance requirements we have mentioned before, we also need to be careful that we cannot delay effect operations into the second stage. Effect operations should be resolved strictly in the first stage, which means the result of this execution function that taken a statement, the result of that is an effective computation that manipulates second stage representation of data. As you can see, the type of the unit, which is the result of the effect computation, and the state underlying the state effect, the store here underlying the state effect are both underlined, meaning they are second stage data. Here it shows an annotated version of the interpretation of assignments. The whole assignment is syntactic and it's a first stage constructor. So it is not underlined. But its value V after the evaluation and the runtime store are both dynamic because they may depend on runtime inputs, and so does the updated store. Here is also underlined. But the functions and operations for retrieving the store are both first stage functions, like the get store, pull store, and also the execution function itself. They are all first stage functions. The stage interpretation of other parts in the language are also similar, but a bit more involved. In the paper, we have detailed discussion of how to stage conditionals and loops, which are omitted in this talk, but please look at the paper for more detail. After this step, we obtain a staged symbolic definition interpreter, which is actually already a compiler, symbolic compiler, in the sense that given an input program AST and also the handlers in the first stage, we can specialize the staged symbolic interpreter and output the code representing the symbolic execution. The generated program is much more verbose, but essentially it is manipulating the stores, accumulating the pass conditions, and performing non-determinism computation depending on our execution strategy. This process of specializing an interpreter with respect to an input program and generating code is known as the first Fussell projection, and notably in our case, the generated code has no overhead of interpretation because the interpreter and syntax dispatch is already executed in the first stage here. It also has no overhead of effective handling because the handlers are also applied in the first stage. At the moment, another way to look at our approach is that this staged symbolic interpreter is an instrumented interpreter with symbolic semantics. And staging this instrumented interpreter produces instrumented code. So in this sense, our approach unifies interpretation and instrumentation based to building symbolic execution in a principled way by staging. You can just build an interpreter and you will get the performance benefit of instrumentation. And with the symbolic runtime here, which provides necessary definitions and operations of symbolic values in C++, we can further compile the output code and link together with SMT libraries and obtain a binary executable symbolic program. If there are still concrete inputs to the program, they will be taken in the second stage execution. And by executing the symbolic program with those concrete inputs, we can obtain the result of symbolic execution, which are usually generated inputs of many passes from SMT solvers. Next, let's talk about how the handlers are used with more detail. First, recall that the effect operations when defining the symbolic interpreter are abstract, which means we have not specified what should we do when encountering those effect operations or how to interpret those effect operations. And effect handlers are programs that provide interpretation of those operations in a modular fashion. For instance, we can define a handler for each category of effects modularly. For example, here we have state effect handler, IO handler, SMT handler, and also non-dat handler. And it is also possible to have different interpretation for a given effect operation. Now, given a program P of our simple imperative language, by applying an execution function exec here, which transforms a program to an effector for computation, and also by composing and applying the handlers for those effects, overall, we can obtain a second stage representation of the execution result, which is essentially a list of symbolic states that including the pass conditions of each pass. More interestingly, because the handlers can access delimited continuations, we can use them to implement different execution strategies over passes, which are in fact different interpretation of the non-determinism effect. For example, in the paper, we discuss exhaustive execution strategies that explore all branches via backtracking, which is the one you may expect and similar to a list monad, but it also can be DFS or BFS. The strategies can also randomly sample a subset of passes to explore by generating a flip coin into the second stage, and more other sophisticated heuristics are also feasible to be implemented using effect handlers. To further evaluate our approach beyond toy languages, we have implemented a prototype for a subset of LLVM-IR that could handle around 20 essential instructions. It is written in Scala and can generate C++ code. We use FreeR monad to embed algebraic effects and handlers in Scala and use the lightweight modular staging framework to do staging and code generation. We also have a simple symbolic runtime that works together with the generated C++ code, which both using the immer library and immutable data structures. The generated code the generated C++ code also directly use STP's C API, which is the SMT solver we used. We also encourage you to read our paper to find our more details on implementations. Using this prototype symbolic compiler for our LLVM-IR, we also have evaluated its performance compared with the end-stage version and CLI. The evaluation focused on pass traversal time, and we use benchmarks that has finite passes to ensure all execution engines explore the same set of passes. Overall, our stage prototype is 10 to 30 times faster than the end-stage version, which is a symbolic definition interpreter written in Scala with FreeR monads. It is much slower due to the overhead of interpretation and effect handling. Our prototype is also 2 to 3 times faster than CLI, which is a popular and mature symbolic execution engine for LLVM-IR. For example, this multi-pass 3 benchmark has over 1 million passes, and the end-stage version could not finish it in 1 hour, so it's timeout. And our stage 2 can finish them in 96 seconds, while CLI uses over 300 seconds to finish them. We also have an end-to-end evaluation on the maze benchmark. This program is much smaller, but also has bounded loops, arrays, and pointer arithmetics. Our tool can still outperform CLI with roughly 2 times faster. And this running time includes the solver time, which generates all the inputs. Overall, here what I show are some micro benchmarks and of unessential and representative instructions. There are also a lot of things can be done to further scale up our approach to real-world and larger programs, such as supporting more instructions and modeling environments such as system calls and library calls. And to conclude, we contribute a novel approach to building symbolic fusion engines by starting from the definition interpreter of the language and by using multi-state programming and algebraic effects. The definition interpreter brings higher confidence in the semantic correctness, and staging brings better performance compared with pure interpretation, and algebraic effects and handlers brings flexibility in terms of path selection strategies. Finally, thank you for your attention, and our code is available on my GitHub repository. Thank you.